Welcome to today's explainer. So, if you've ever stood next to a colossal cargo ship or an ocean liner and just wondered, how on earth does this massive mountain of steel actually stay afloat, let alone move so gracefully across the ocean? Well, you are in exactly the right place. Today, we're going to build a mental blueprint of a massive ship, starting from the outside and working our way in. We are going to break down some seriously complex naval architecture terms and make them absolutely impossible to forget. By the end of this, you won't just look at a ship, you'll actually see the intricate physics and the genius design that make it all possible.
Okay, let's dive right into this. Here is our top-down roadmap for how we'll construct our understanding today. First, basic dimensions. Second, weight and tonnage. Third, anatomy of the hull. Fourth, propellers and movement. And finally, the physics of stability.
Starting off with Section 1, the ship's basic dimensions.
Now, you might be wondering, how do you even measure something that big? Well, when we talk about a ship's length, naval architects don't just throw out one single number. They actually use two very distinct measurements. First is length overall, or LOA. This is the extreme physical length. We're talking the absolute furthest point of the bow to the absolute furthest point of the stern. But then you have length between perpendiculars, or LBP, which is a bit more, well, structural. It's measured between two imaginary vertical lines drawn straight through the forward and aft parts of the ship, exactly where it meets the waterline. So basically, LOA is about the physical space the ship takes up when it's at a dock, while LBP is absolutely crucial for calculating how the ship interacts with the water. A really easy way to remember this, just think, LOA is for parking and LBP is for physics. Moving on, let's look at how we measured the width, height, and underwater depth, which are known as breadth, depth, and draft. There's a really important pattern here between extreme versus molded measurements. Extreme measurements always go to the absolute outermost boundaries. So, extreme breadth measures to the outside of the shell plating. Extreme draft goes down to the very lowest point of the hull. But molded measurements? Those are just for the internal skeleton. Molded breadth stops at the inner strakes of the shell plating, and molded draft only goes down to the top of the keel. To lock this in your memory, just remember extreme is the dimension the ocean has to deal with, and molded is the framework the builder deals with. Actually, let's scratch the idea of a ship being a perfect flat, blocky rectangle. It has these highly intentional curves designed to improve seaworthiness and shed water. First up is camber, which is the transverse curvature of the deck. Basically, the deck is higher in the middle than at the edges, so water just naturally runs off the sides. Then we have shear, which is the fore to aft upward curve. This makes the bow and stern higher than the middle, completely essential to stop massive waves from swamping the deck. Next is tumble home, which is this sleek inward tapering of the hull above the waterline. And finally, its total opposite is flare, the outward curving structure at the forward end. That flare pushes water away and gives the crew extra space for all that heavy anchor machinery.
Let's move to the next logical step in our blueprint with Section 2, weight, volume, and tonnage.
So everything we're going to discuss regarding a ship's weight is completely anchored to the Archimedes principle. It states that when an object is immersed in a liquid, the upward buoyant force it experiences is exactly equal to the weight of the fluid it displaces. Simply put, for a massive steel ship to float, it literally has to displace a mass of water equal to its own total mass. If a ship weighs 50,000 tons, it has to carve out an underwater hole that perfectly fits 50,000 tons of water. Pretty incredible when you think about it. So how do we actually categorize all that weight? We divide it into lightweight and deadweight. Lightweight is the mass of the naked ship. It's the completely empty vessel with all its steel structures, decks, and machinery, but absolutely no cargo, no fuel, no crew, and zero ballast. Deadweight, on the other hand, is the moneymaker. That is the maximum weight a ship can safely carry. The sum of all the fuel, cargo, stores, and ballast. Deadweight is the burden the ship bears. Lightweight is just the ship itself. The easiest way to remember this? Think of lightweight as the weight of your empty backpack, and deadweight as all the heavy textbooks you stuff inside it.
Now here's a fact that trips a lot of people up. Let's see how weight translates into volume, which is confusingly called tonnage. Remember this, in naval architecture, tonnage measures space, it does not measure weight. Gross tonnage, or GRT, and net tonnage, or NRT, are measures of internal volume. Gross tonnage is the measure of the ship's overall internal space from the keel all the way up to the funnel. That includes both the earning spaces like cargo holds and non-earning spaces like the engine room and crew quarters. Net tonnage, however, strictly measures the volume of just the cargo spaces. It's the physical space that actually generates revenue for the shipping company.
Obviously, if you load cargo, the ship sinks deeper into the water. But exactly how much deeper? That's where TPC, or tons per centimeter, comes into play. This little formula calculates the exact mass required to increase the ship's mean draft, which is its depth in the water, by just 1 single centimeter. You take the area of the water plane, multiply it by the density of the water, because, denser salt water provides a lot more buoyancy than fresh water, and then you divide by 100. It's this brilliant, beautifully simple piece of math that prevents officers from accidentally overloading the ship and sinking it below safe limits.
All right, zooming in now. Section 3, Anatomy of the Hull.
So the hull itself is made of these long rows of steel plating, which are called strakes. And there are a few key players here you definitely want to memorize. First, the garboard strake, which guards the bottom keel. Then there's the shear strake right at the top deck, named because that's where waves shear across the vessel. At the very back, the coffin strake connects to the stern, literally the dead end of the ship. Up at the front, the rows converge to kind of steal space, and that's known as a stealer strake. And finally, the bilge strake, which curves right at the bottom corners where the vertical side meets the flat bottom. Now imagine taking a massive wave over the deck. That water has a huge amount of dangerous top weight, and it has to be cleared instantly. To do this, we use two main drainage methods. A freeing port is simply a large, direct opening cut straight into the lower portion of the solid bulwark wall, and it just allows deck water to wash directly overboard. A scupper, however, is a gravity deck drain. It's connected to a piping system that leads all the way down through the ship and out the side shell. Think of it this way. Freeing ports are like opening a massive door to let a flood out, while scuppers are much more like your standard bathroom sink drain.
Moving from the sides to the very front of the hull, I guarantee you've seen this feature before. It's that strange protruding bulb right under the waterline at the bow of really large ships. It's called a bulbous bow. Now, intuitively, it looks like it would create a ton of drag, right? But it actually drastically reduces resistance by modifying how the water flows around the hull. In calm waters, this ingenious design reduces pitching, increases buoyancy, boosts speed, and significantly slashes fuel oil consumption. It is a real game changer.
Down inside the bottom of the ship runs the duct keel. This is a watertight tunnel used to inspect pipelines. But because it's a tight, enclosed space, entering it without following a strict checklist is incredibly dangerous. To commit this safety protocol to memory, just follow these 4 non-negotiable steps. First, open the inlet and outlet ventilation flaps. Second, start the duct keel fan from the control room. Third, crack open the entry hatch and wait a mandatory 15 minutes for fresh air to circulate. And fourth, you absolutely must have a standby person stationed at the entrance at all times to communicate with the person inside. You never, ever break this protocol.
Shifting to the aft end now with Section 4, Propellers and Ship Movement.
Propellers are honestly master classes in fluid dynamics. Let's define the 4 main traits that make them work. Rake is the forward or aft tilt of the blades when you look at them from the side, and this allows for clearance between the spinning blades and the hull. Skew is the sideways twist or bend in the blades, which is there to reduce unsteady pressure forces and vibrations. Then you have pitch. Pitch is a theoretical distance. It's exactly how far forward the propeller would travel in one single 360-degree revolution if it were screwing into solid wood. But water isn't solid wood, which naturally brings us to slip. Slip is simply the difference between that theoretical pitch distance and the actual, much shorter distance the ship truly travels because the water yields to the blades.
And finally, the most vital part of our blueprint, Section 5, the physics of stability.
Now, what's really interesting about this is the elegant dance of invisible forces keeping the ship upright. Let's talk about 3 specific points. First, G is the center of gravity. That's where the entire downward weight of the ship acts. Then B is the center of buoyancy, which is the center of the underwater volume pushing forcefully upward. When a ship heels over, that B point shifts. If you were to draw a vertical line straight up from the new B, it intersects the center line at M, which we call the metacenter. Here is the absolute golden rule. For a ship to be stable and return upright, the metacenter M must always be above the center of gravity G. The distance between those 2 points is known as the metacentric height, or GM. So the absolutely crucial point in ship design is getting that GM distance just right. If too much heavy cargo is placed at the very bottom of the ship, the center of gravity drops, creating a huge GM. This makes what we call a stiff ship. It's overly stable. That sounds good, right? But it means if a wave pushes it over, the righting moment is so aggressive that it violently snaps back upright, which can easily damage cargo and injure the crew. Conversely, if too much weight is placed high up on the deck, the center of gravity rises, creating a very small GM. This is a tender ship. It lacks sufficient stability, so when it gets pushed over, it has this long, slow, agonizing roll back to upright. You want the Goldilocks zone, neither too stiff nor too tender.
So how does shipbuilders determine that exact initial GM on a freshly built vessel? They perform this elaborate procedure called the inclining experiment. But for this to work, the conditions have to be absolutely perfect, like a science lab. The ship must be completely empty of cargo. All mooring ropes have to be slackened so they aren't artificially pulling on the ship. Tanks inside must be either completely empty or pressed completely full to stop water from sloshing around, and the water outside the ship must be perfectly calm and sheltered.
Once those conditions are perfect, they set up special tools called stabilographs. These are heavy metal pendulums used to measure really tiny angles of heel, and they place one forward and one aft. Next, they place 4 massive, known weights on the main deck, 2 on each side. Then, they systematically move these masses from one side to the other. By recording the exact weight moved, the exact distance it moved across the deck, and reading the incredibly subtle deflection on the stabilograph, they can calculate the exact position of the ship's center of gravity. It is a marvel of applied physics.
Which leads us to a fascinating and kind of scary concept, the angle of law. This is the terrifying angle at which a top-heavy, unstable ship naturally flops over and just rests there, suspended dangerously between sinking and righting itself. It can only be corrected by very carefully lowering the center of gravity. It makes you think, if perfectly understanding these exact dimensions and structural definitions is what keeps a multi-million-dollar ship afloat, how might identifying your own angle of law, those areas where things have gotten a bit too top-heavy or unstable, help correct imbalances in other engineering systems or, even in your own life? Lowering your center of gravity, bringing things back to basics. It's a structural blueprint that goes far beyond the shipyard. Thanks so much for joining me on this explainer, and remember, keep your meta center high.